Okay, so I know a lot of you guys are pretty much absent because of the World History test. So I wanted to go through the notes. You're still responsible, so you've got to watch this. It will definitely help you understand what's going on because remember, at the end, we're going to have a test over all this bonding stuff. And secondly, I put some notes at the end to help you with your homework. So if you look at the agenda for the day, you can see that you have section 12.2 homework due. Okay, that's due next class. For most of you, that means tomorrow, right? Because guess what? Today's Thursday already. Actually, not most of you, pretty much all of you, except for D block, which is due today. So let's take a quick look at the warm-up and objective. All right, so you still need to write this down in your notes so you have warm-up number 8. So we're going to learn about what is called stable electron configurations, the localized electron model of bonding, and we'll talk a little bit about the size of ions and also what polyatomic ions are, just a little bit. Then we'll finish with the homework. Now, question is, what does a noble gas electron configuration mean? Now, it's pretty straightforward. If you take a periodic table out and look at it, what you will see, every noble gas has, in the period that the atom is found, the element is found, the S and P electrons are completely filled. That means it's got 8 valence electrons. So take a moment, write that down. The electron configuration matches that of a noble gas, and that means its outermost S and P orbitals are completely filled. Those are the ones that are found in the period in which the element is located. As an example, neon, second period, it's completely filled for the 2s electrons, so 2s2, and completely filled for the 2p electrons, 2p6. That's 8 valence electrons, completely filled. Now, what you're going to see in your textbook is you'll have some questions about stable electron configurations or electron configurations that look like a noble gas. So we already know that the S and P orbitals are going to be completely filled when a metal and a nonmetal form an ionic compound. That is the stable state in these. Why do we know that? We already talked about this way back at the beginning of the year when we talked about how compounds form, ionic compounds form, and we used rings, and you saw that in the metals case it loses electrons to lose a ring, and in the non-metals case it fills the ring. Well, we're not using rings now, we're using orbitals, but it's the same process. So if you take a look at the textbook, you will see, if you look at the electron configuration, now these are all shorthand for some different elements. 1, 2, and 3 are metals. When they form ionic compounds, they lose 1, 2, or 3 electrons. By the way, if you're wondering what the group number is here, really in our periodic table, that's group 13, that's group 16, and that's group 17. Our periodic table uses numbers 1 through 18, so slightly different numbering. So take a look. Sodium normally has 1 3s electron. In order to form an ionic compound, that 1 3s electron is going to be transferred to the nonmetal, and the resulting ion is going to look like neon. So sodium 1 plus looks like neon. Magnesium loses 2 electrons, and look where it is. It will end up looking like magnesium 2 plus will end up looking like neon. Aluminum loses 3 electrons. It will end up looking like neon. So those are all the noble gas configuration, one period above where these elements are found. These are all found in the third period. Now, if you go up to the second period and look at oxygen and fluorine, look at their their electron configurations. So you see that they're like helium, except then oxygen has got 6 total valence electrons. Fluorine has got 7 total valence electrons. So oxygen has 2 holes that need to be filled in order to get it to have a completely full 2s and 2p orbitals. When they're completely filled, it looks like neon. So it will acquire 2 electrons and be 2 minus charged. Fluorine only has 1 hole. It will acquire 1 electron. So fluorine 1 minus will now also have the same electron configuration as neon. Now, stable electron configuration is one with the valence electrons in the s and p orbitals are completely filled. All atoms in a compound, doesn't matter whether it's an ionic compound or a covalent compound, have stable electron configurations. That is, all their s and p orbitals are full. They have a total of 8. That is 8 electrons. This happens during bonding. How? Well, if you've got oxygen, all right, which has, without the 2 blue down arrows, has 2 holes. You see it's got 2 half-filled p orbitals. And if you look at hydrogen, hydrogen itself also only has 1 half-filled s orbital. But when they overlap, as you're going to see, we're going to talk about this in the next slide, if you overlap a hydrogen s orbital with an oxygen 2p orbital, you end up basically filling all the orbitals. So if you do that twice, you'll end up with a completely stable electron configuration of valence electrons for both oxygen and hydrogen. Now, this is what our model of bonding is. It's called the localized electron model of bonding. And that states that covalent bonds form when half-filled atomic orbitals of 2 atoms overlap. So again, our electron configuration of oxygen has those 2 holes. Our electron configuration of hydrogen has 1. And so if you're going to put oxygen together with hydrogen, well, if it's got 2 holes, it needs 2 electrons, 1 for each. Each can get 1 from a hydrogen, so you're going to need 2 hydrogens for every 1 oxygen. Here's another picture of the same thing. Now what I've done is I've completely ignored writing the 2s2 electrons for oxygen. The 2s orbital is already completely filled, so it's not really involved in bonding. But oxygen does have 4 total electrons in its 2p orbitals. Now this vertical one I call 2py, just labeled it that, and you notice it's got 2 electrons in it. Now you got to keep in mind, one has to be up spin, one has to be down spin because they're in the same orbital, but they aren't really separated like this. There could be 2 in the top portion of the p orbital, there could be 2 in the bottom, the down one could be in the top, the up one could be in the bottom. They're basically zipping back and forth. Now 2pz is this one, 2px is this one. Now you notice I drew that like a flower. I can't really draw 3-dimensional. This is actually a 3-dimensional shape. But if you look at 2pz, there's 1 electron. Again, it's an up arrow, just like 2px, and it's zipping back and forth between the 2 halves of the pz, and the 2px electron is zipping back and forth between the 2 halves of the px. Now, hydrogen just has a spherical orbital with 1 electron. It's got a 1s orbital. Now, in order to form a bond, we're going to need to overlap the hydrogen orbitals, 1s orbitals, with our 2pz and our 2px. So once we overlap them, this is what we get. Do you notice now that everybody's got 2 electrons? The 2pz still has 2, the 2py still has 2, the 2pz, which is at this angle, now has 2, 1 from oxygen and 1 from hydrogen, and the 2px now has 2, 1 from hydrogen and 1 from oxygen. So, like I said, we don't see the 2s2 electrons of oxygen in this picture, but when we're all done and this forms water, our oxygen has a 2s2, 2p6 electron arrangement. That is a noble gas arrangement. Hydrogen now has a 1s2 arrangement. That's like helium. That's a noble gas arrangement. So that's the most stable way that these things can be constructed. Now, we have names for some of these bonds. In the localized electron model, sigma bonds refer to single bonds, and they result from end-to-end overlap of, let's see, 3 possible things. Could be 2 s orbitals overlapping, it could be an s and a p overlapping, or 2 p's overlapping. Now, when they overlap, those atomic orbitals are kind of renamed molecular orbitals, but for the most part, they behave by the same rules. In other words, by the same rules, I mean molecular orbitals can only have 2 electrons in them, and one has to be up and one has to be down. So here's a picture that shows this overlap. Two s orbitals, each having one electron of two separate hydrogens, will form a compound, and then you'll end up with a distribution of those bonded electrons. Mostly they're in between. The ends of two p orbitals can overlap to form a sigma bond, and you'll end up with this kind of odd structure, but mostly the electrons are going to be in between the two nuclei. You can also have this final structure where you have an s and the end of a p orbital overlapping, and you end up with a structure like this. Here's your hydrogen, the other nuclei would be over here somewhere. So overlap of two s orbitals give us a sigma bond. Overlap of an s orbital with the end of a p orbital give us a sigma bond. Or end-to-end overlap, which is shown in B, of two p orbitals will give us a sigma bond. Now, what's a pi bond? A pi bond results from side-to-side overlap of two p orbitals. This results in areas of electron density above and below the bond axis. So this is what it looks like. So here you've got a p orbital on one atom, another p orbital on another atom, and they get close to each other. They can form a bond, and you notice that the electrons in those p orbitals now no longer look like dumbbells. They look like two sort of odd-shaped ellipses above and below the axis of the bond. So for instance, if you have an oxygen molecule, right? Two oxygens covalently bonded to each other. What you end up with is one sigma bond, and that sigma bond will come from end-to-end overlap of two of the half-filled p orbitals, one from each oxygen atom. And the other bond you get is a pi bond, and that results from the side-to-side overlap of the other half-filled p orbitals on each of the oxygens. Now if you go over here where you've got something that's got a sigma and two pi's, this is a triple bond. This is known as a double bond. If, for instance, if you have nitrogen, nitrogen has three electrons in the p suborbitals, one in each of the x, y, and z. So when nitrogen forms a compound with itself, you end up with two nitrogens triple bonded together. You get one sigma bond, which is an end-to-end overlap of two p orbitals, and you get two pi bonds, which is side-to-side overlap. So a triple bond is one sigma and two pi, a double bond is one sigma and one pi, and you cannot ever form a quadruple bond between two atoms. Now that doesn't mean you can't get an atom forming four bonds, but it can't form four bonds to another atom. That's not allowed. Spatially, it's impossible, okay? It's spatially not allowed and can't happen. Now, what about ionic bonds? So in our ionic bonds, metals are losing electrons, nonmetals are gaining. Talked about this a bunch of times. And they're still going to end up with a noble gas electron configuration. So for instance, if you look at sodium, it looks like neon with a 1s, extra 1s electron. And if you look at fluorine, fluorine looks like neon missing one electron. So guess what happens if you get sodium next to fluorine? Fluorine will grab this 3s electron, fill its last space here, and then they both, guess what they look like? They both look like neon. Now this is just trying to show it with the orbitals drawn out. Here is your 2s orbital, which is a sphere, 3s orbital, which is a sphere. And when that electron jumps over and fills the last space in the 2pz, you form an ionic bond. Fluorine has a 1- charge. It has an electron configuration of neon. The sodium lost an electron. It has a 1+ charge. And it also has the electron configuration of neon. So when they're both done, they both look like 1s2, 2s2, 2p6. Okay? Hopefully this is making some sense. Now what about ions? Now this is actually the most logical thing to figure out. It's pretty easy. So atoms, right, are neutrally charged. If you're a metal, when you form ions, you lose electrons. When you lose an electron, for instance, this is the atomic size of alkali metals, you notice they get smaller. So there's kind of two reasons. One, because lithium has 2 energy levels, and the energy levels stack. Lithium with a 1 plus charge has lost its second energy level, so it's smaller. And now you've also got 3 protons holding onto 2 electrons, which will contract them. Sodium in the third period. All right, so sodium has got 1 electron in the 3s energy level, the third energy level. When you remove that electron to form sodium with a 1 plus charge, there's no longer any electrons in the third energy level. It's much smaller. And again, you've got 1 more proton in the center. You've got 11 protons holding on to 10 electrons, so it will pull it closer. So when things form cations, when metals form cations, their diameter gets smaller. Conversely, when nonmetals gain electrons to become ions, now you've added an electron. Now you've got fewer protons than electrons, so you can't hold them as tightly. Fluorine has 9 protons. Fluorine with a 1 minus charge has 10 electrons. You can't hold them as tightly, so it gets bigger. All right? Cations, metals get smaller. Anions, nonmetals get larger when they form ions. Last little comment that I wanted to make about were polyatomic ions. Polyatomic ions are held together by covalent bonds, but the whole polyatomic ion itself has the charge. So for instance, here's a ammonium ion, here is a nitrate ion. The ammonium has 4 nitrogen-hydrogen covalent bonds. The nitrate has 3 nitrogen-oxygen covalent bonds, but the entire structure has a charge and it won't fall apart in water. In other words, you put ammonium nitrate in water, it will form ammonium ions and nitrate ions, but the individual polyatomic ions do not break apart. Now here's a little bit of homework help. Okay, let's look at question number 4a first. It says you need to write out the electron configurations in shorthand for each element. That's the best thing to do. Now take a look. You got magnesium, you got sulfur. Sulfur has 2 holes. It's 2 holes, 2 electrons away from filling its p orbitals, which will make it look like a noble gas. Magnesium, the best way to get to a noble gas is to lose those 2 electrons. So you figure out the easiest way to get there, and that is removing 2 of the 3s electrons from magnesium to fill the 2 holes in the 3p4 orbitals of sulfur. And when we do that, magnesium 2 plus looks like neon, and sulfur 2 minus looks like argon. And they both have noble gas electron configurations, and the formula must be magnesium sulfate. Why? Because for 1 magnesium losing 2, 1 sulfur gains 2, and then they stick to each other through electrostatic attractive force. Now let's take another look at one of the other questions. First, for question number 6. When they say groups 1, 2, 6, and 7, they really mean 1, 2, 16, and 17 on our periodic table. Now, we all have to get them to the electronic configuration of argon, and the only elements we can use to do that are in 1, 2, 16, and 17 are potassium, calcium, sulfur, and chlorine. Then we write out the complete electron configuration of argon. That'll be the common electron configuration, so write it all out. And then finally, when you're asked to write out the symbol with the charges, they just mean the ion symbol. Here is an example. Now, this isn't one of these 4, but if you, for instance, look at the common ion of oxygen, oxygen gains 2 electrons, and so the symbol with the charge is O2 minus.